Today is our first lecture. We're going to be talking about Newtonian dynamics. Newtonian dynamics is a really important topic. It's going to be foundational to a lot of our studies here. In our definition, we define Newtonian dynamics as the motion of particles and their interaction with forces. So when we talk about Newtonian dynamics, we have one really fundamental equation that we're concerned with, and that's the equation that F equals ma. And for our purposes, it's very useful to express this equation in terms of a differential equation. So the way that we do that is we say that our acceleration is the time derivative of our velocity, and our velocity is the time derivative of position. And using these two equations, we can express this equation in very useful ways that can allow us to solve systems. And we'll demonstrate that next. All right, so now that we've discussed this, we're going to move on to an example. So here we have a mass spring damper that's moving only in the x direction. And using these equations, we can write the system and solve it. So what we're going to do is we're going to first write the forces. So in this system, we have a spring, and we know that the force of a spring is equal to negative k times this displacement x. And this k is just the spring constant for this spring. Then we can, of course, write that's equal to ma. So we have negative kx is equal to ma. And like we discussed before, we'll rewrite this a in this differential form. So what we're going to write is m d squared x dt squared is equal to negative kx. And now all we have to do is solve this equation in terms of x to get an analytical solution. So what I'm going to do is divide by m here, and we'll have d squared x dt squared is plus k over m x equals 0. And often we'll see this term here is called the equation of motion. So when we have all of our terms on the left-hand side equal to 0, that's typically what we denote as an equation of motion. Another thing that we can do here is instead of writing it in this form, oftentimes we'll see something that looks like this, where we just say x double dot plus k over mx is equal to 0. This is an equivalent way of writing the same thing. We're just replacing the second order derivative by 2 dots. And if we had a first order derivative, that would be 1 single dot. So now we can solve this system. I'm going to skip over how we do that. I'm just going to present the solution. It's just some simple differential equations, but we can get this equation in terms of time, and we can say that the solution is sum a times sine of square root k over m times t plus sum b times cosine of square root k over m times t. So this is just a basic example that's showing how we can use this differential equation form to get an analytical solution for what x is over time. What we're going to do now is show an example where this kind of breaks down and we have to use some other methods to solve this equation. All right, so now that we've done our mass spring damper, we're going to move on to something a little more complicated with this rocket example. So we can see here with this rocket, we have a thrust force, a drag force, and a gravity force. And this is all in 2D space, so this is a little more complicated than the example we just discussed. We'll still start by doing the same thing. We'll take all of our forces and we'll add them together. So we can say that our forces are this thrust force minus this drag force and minus gravity. And I'm just going to write gravity as mg. And of course, these are all still equal to ma. One thing that we'll note in this example that's a little bit different than what we just looked at is if we expand out this equation, we can actually write our drag force like this. So 1/2 rho v infinity squared s cd. So these terms in this equation might look a little confusing. Rho is the density of the air. V infinity is this free stream velocity. So this is just the speed of the air that's moving past the rocket. S is some area that we define. Typically for a rocket, this S is going to be that cross-sectional area of this diameter. And then CD is a function that's just our coefficient of drag. That just lumps all of these really complicated aerodynamics into one number that describes how draggy our object is. The important thing to note, though, is that in this equation, we have v infinity here. And on this right-hand side, if we write this in terms of the differential form, we have dv dt. So we have something kind of interesting in this problem. We have a velocity on this side, and then we also have a velocity on this side. And what makes this really complicated is if we want to solve this, we need to know what this v infinity is to calculate this drag. So it turns out we actually can't solve this very easily. And for some problems like this, there's actually no analytical solution. We can't do those integrals or differential equations like we did for the mass spring damper. So we're going to have to take a little bit of a different approach here. And what we're going to do in this case is we're going to think about doing this in small chunks of time. So if we think about what our velocity is going to look like over time, what we can do to get an approximate solution is we'll say, let's start at time 0 when the rocket's on the ground. When the rocket is on the ground, we know that our initial velocity will be 0. So we know we're starting at this point here. And then we'll say, let's go forward a tiny bit in time and assume that there's no drag because our velocity is 0. So we have our thrust and we have our gravity, and we're just going to use those to find what our new velocity is. And say we get something that looks like this at time t1. So now what we're going to do is we're going to go back to this equation and say, well, our velocity is now, say, 10 meters per second. And we're going to plug that in for drag, and then we're going to recalculate this. And we'll get something a little lower because now we have drag. And we're going to keep doing that, and we'll get our velocity as a function of time. But now we're doing this in discrete time rather than in continuous time like we did with the integral. So we can express this mathematically. We just do some rearrangement of this equation. So we're going to write the same thing down here. But now what we'll do is replace this dv dt by delta v by delta t. So this is the same thing that we said here. We're just discretizing this equation, and we're doing that by replacing this dv dt by delta v delta t. So now to solve this equation, we're going to move delta t over to this side. So we have f of t minus f of d minus mg. All of this times delta t is equal to that delta v. I'm going to do one final rearrangement here. Knowing that delta v is this v final minus v initial, we can do a final rearrangement of this equation and say that our v final is this part of the equation plus vi. So we'll have vi plus everything that we wrote here. F of t minus f of d minus mg, of course, times delta t. So this is a really important thing that we've just done, and we call this the Euler's method of integration. So this Euler's method is one of the basic ways that we can solve these differential equations that we don't have analytical solutions for. And obviously for our rocket, we don't have an analytical solution, so we're going to end up using things like the Euler's method a lot. This has some pretty important implications. What we've just described is one of the simpler ways that we can do this. In future videos, we're going to talk about more complicated methods to do this. One drawback that you might notice with this is if this delta t gets really large, this graph, we're going to have some large, kind of roughness in this graph, and it's not going to look very good. So using some other methods, we can use larger time steps and get better results. But that's beyond the scope of what we're talking about in this video. Additionally, some future things that we'll talk about some more governing equations other than just F equals ma that we can use for rotational dynamics and other subjects. But as far as we're concerned with today, this is everything that we're discussing, and really the main thing that we want to talk about is this Euler's method and how we can use this discretization to get an approximate solution to differential equations.